If you think back to Calculus 1, there was a geometry problem that sort of got the whole thing started and inspired everything that you learned in that quarter. And that geometry problem was the problem of finding the slope of a tangent line. Well, there's another classical geometry problem that will serve as a starting point for us this quarter, and that's the geometry problem of finding the area under a graph. So what I have in mind here is, suppose we have the graph of some function, f of x, and we have a couple x values in mind, say a and b, and what we want to find is the area under the graph between a and b and above the x-axis. So, in general, this is a very tricky problem because, the left, right, and bottom of this region are straight lines, but the top could be any shape at all, really, as long as it's a function. If your function happened to be also a straight line, then the region that you get would be a triangle, and we have some hope of finding what this area is. But if this function is at all complicated, the top of this region is going to be some wavy, wiggly thing, and we aren't going to have any nice formula for what the area of this kind of shape should be. So it's actually a pretty difficult problem. And we're going to actually approach this problem in the same way as you approached finding the slope of a tangent line back in Calculus 1. And that's sort of a three-step process. So the first step is just to give up. This problem is too hard. It's too hard to sort of tackle in its full generality all at once. So we're going to start by just giving up on solving the problem exactly and instead solve the problem approximately. And then once we've solved this problem approximately, once we have some nice approximation for what this area is, that depends on at least what this function is and what these endpoints are, once we have a nice approximation, then we will think, how can we make our approximation more exact? And if we can make our approximation more exact, then maybe, hopefully, we can make it more exact and more exact and more exact until eventually it turns into not just an approximation anymore, but actually the exact area under the graph. So that's the hope. And this is actually the same thing that we did when you found the slope of a tangent line, right? If you want to know the slope of a tangent line to some graph, right, here's the tangent line. Well, the very first thing you did was you give up on the tangent line, and instead you have a second point, right? You find the slope of this nearby secant line, which is not the tangent line, but hopefully it's close. And then you make this approximation better by sliding the second point closer and closer to the first point, which makes the secant line closer and closer to a tangent line, and that's how you make your initial approximation more exact. So, even though this strategy seems a bit weird that you pose a problem, give up on the problem, and then hope to recover an exact answer, even though it may seem strange at first, it actually has worked already when you found slopes of tangent lines by using secant lines and then taking a limit. So that's what we'll do. We'll somehow come up with an approximation for area and then have some process to improve our approximation. And you can bet that this process will somehow involve some kind of limit. And that's how we'll attack this area problem. But before we actually do that, I want to point out that this area problem, it seems like maybe of limited interest. I mean, finding areas is nice, but it seems like how often do you need to know the area of a region like this? Well, it turns out that actually there are lots of questions that you can phrase in terms of finding an area. So let me show you just one. Suppose that we have a function that is the velocity of some object as a function of time. So here we have time, and this is probably going to be in seconds, and then the vertical axis is going to represent velocity, and this might be in meters per second. What would an area represent on this kind of graph? Well, the units for area on this graph, well, area units are always the units in the horizontal direction times the units in the vertical direction, because area is just horizontal and vertical. In this situation, the units in the horizontal direction are seconds, and the units in the vertical direction were meters per second. And then if you simplify this unit expression, what you get is just meters. So the units for area in this velocity versus time graph is actually represents some quantity in meters. And what sort of quantity, if you have an object moving around, what sort of quantity is measured in meters? Well, it's the displacement of the object. In other words, how far it moves between time A and time B compared to where it started. So in this situation, the area actually represents a quantity that you might want to know. And in fact, this always turns out to be the case. If you have any graph, the units for area are just your vertical units times your horizontal units. If your vertical unit is a rate and your horizontal unit is time, then area will represent whatever the units are in the numerator of this rate. So if you have a function that is any sort of, say, a flow rate or a population growth rate, then area is going to represent a volume of liquid that has flowed, or a number or a change in population over time. So finding an area actually has lots of applications depending on or if your vertical coordinate is actually a rate. So for that reason, we will find lots of situations where finding an area turns out to be a very useful operation. So with that in mind, let's go ahead and see what kind of tools we need to make progress on writing down an approximate area.